So let's maybe get started. Um, s- okay. Thanks for coming to our talk. Today, Jimmy and I will talk about NeMo-Aligner, a scalable toolkit that we built for model alignment. I'm Gerald. I'm the framework lead for NeMo-Aligner, and Jimmy is the perf lead for NeMo-Aligner. So to start, I first want to talk about the NVIDIA's end-to-end LLM software ecosystem that we built. So everything here is open source, and NeMo-Aligner falls inside the NeMo framework more broadly. So NeMo framework is essentially a core component of our LLM training stack where it focuses on very high performance pre-training. And as part of that, Aligner builds on top of everything we're using, such as Transformer Engine, Megatron Core, which Megatron-LLM uses, and we build on top of that to do efficient alignment. This involves using parallelisms and high-performance training kernels, and as well, we also take advantage of the inference stack that we have in NVIDIA, in particular TRT-LLM that Jimmy will talk about later on. So to motivate why we need to build a framework, I want to go through the definition of alignment. Alignment, broadly speaking, is getting foundation models to follow instructions and generate human-preferred responses. And nowadays, almost every model that comes out undergoes some alignment stage. To demonstrate what the alignment stage does to a model, I could, let's say, have a query that is such as how many units are in a dozen. And the pre-trained model, let's say 3.1 AB base, would sort of know how to answer this question, but it's not generally easy to read, and it sort of just blabs on the answer over and over again. Whereas if you look at the instruct model, let's say 3.1 AB instruct, its response is short, concise, and just generally what I like to see out of a model that comes out. So what NeMo-Aligner is doing is creating a toolkit to go from the models on the left and turn that into models on the right. For NeMo-Aligner, we want to implement state-of-the-art alignment techniques while also making sure that our performance and scalability are great. So by state-of-the-art techniques, we sort of say have RLHF, DPO, RPO, constitutional AI, SFT. And while we implement this, we sort of want to make sure that the performance and scalability are also great. This involves using model parallelism, doing accelerated inference, which is what Jimmy is going to talk about next, having FP8 support, and we're currently working on long sequence support and sequence packing. Also, we want to make sure that the open source community can sort of use the toolkit easily, so we open source the data sets that we've used for some of our alignment pipelines, let's say HelpSteer and HelpSteer2 and Derning and Eater. We also open source commercially available model checkpoints, which include the 340B instruct and the 340B reward model that was trained with NeMo-Aligner. So to sort of double click a little bit, I want to talk about the performance optimizations that we have been doing, and in particular for the RLHF pipeline. So RLHF stands for reinforcement learning from human feedback. And this is sort of the algorithm that got us from to ChatGPT, essentially. This is prescribed very similar to the InstructGPT paper, and it involves generally 3 steps. So the first step is the supervised fine-tuning step. And this is what happens when you take your pre-trained model, let's say 3.1 base, and ask humans to, let's say, generate what the model should have said. So you give it a question, and the human will write out what exactly to say. And then in this stage, we sort of just like train on this annotated data. And this could get you pretty far, but if you want to have even more performant and a more aligned model, you would go and collect this thing called a preference data set. The preference data is essentially, given a prompt, we have 2 responses, and sort of the human labeler will pick which response is better than the other. And with this preference data in mind, we could go and train a reward model. And what this reward model that comes out of would do is it would assign high scores for responses that it deems as good and low scores for responses that it deems as bad. With a reward model in mind, we could go and plug this into a very canonical RL process, and which is what we talk about when we say PPO. So in PPO, we have, let's say, our policy network, and this is like the GPT that we want to turn to ChatGPT, and we have a bunch of prompts. and we sort of go and use this against the reward model to do the whole RL process. One thing I want to keep in mind is even though we're talking about just the RLHF performance, generally these optimizations would apply to all online algorithms like rejection sampling and other RL algorithms. But we just focus on RLHF because that's the most well-known. To talk more about step 3, we sort of have this kind of like a messy diagram here. But roughly what happens is that we have the policy network, which is a network that we want to turn to ChatGPT. We sample from this policy network, and we ask the reward model to say how good it is. Roughly speaking, when we do RL, we're just trying to increase the likelihood of the good response and decrease the likelihood of the bad response. But in RLHF, it's slightly more complicated than that because we have this thing called the initial policy and the value network. So these two things are mostly here to stabilize training. In particular, the initial policy is to prevent deviations that are too far from the initial model, and the value network is here to stabilize the RL training. In here, and Jimmy will talk about this later on, we have two distinct stages in the RLHF pipeline. One is sort of the inference stage, and that's when we generate samples and run inference on all of these models. Once we finish the inference, we have this thing called a rollout buffer, which caches the generated results, and then we go and do training. So one unique thing about RLHF is that we have inference stage and training stage, and this is part of the greater training pipeline. In contrast with pre-training, we just really do training, and during evaluation, we're almost like just doing training without gradients. But here, we're actually doing autoaggressive sampling and inference on many different models. So as you can see, RLHF is complicated, which means that optimizing the performance of RLHF is also complicated. First, we need to orchestrate 4 different models on the previous slide: the policy, the initial policy, reward model, and the value model. And these 4 models could be of any size, let's say 4 or 5e. One thing to note is that the policy network and the initial policy are architecturally very similar, and the reward model and the value network are also architecturally very similar. So for Aligner, what we're trying to do is we want to make sure that it's as fast as possible, and we want to make sure that we're the fastest open source RLHF implementation. To do this, we have 3 key performance optimizations. 1 is distributed architecture, 2 is TRT-LLM fast inference, 3 is dynamic load balancing. And I'll let Jimmy talk about these 3.
Hey everyone, I'm Jimmy. I was the perf lead for NeMo-Aligner. And yeah, I'll be doing a sort of flyby of all the perf optimizations we do to make RLHF fast. So the first perf feature I'll be talking about is sort of our general architecture to how we implement RLHF. So in NeMo-Aligner, when we launch a job, we launch 2 jobs per each RLHF run. So we'll have one job that holds the value and reward model, and we'll have another job that holds the policy and initial policy. And the reasoning for this is that it maximizes performance. Generally, when you do RLHF, you might have like very differently sized reward and policy models. So for instance, your reward model might be like a really big model, like Llama 4 or 5B, and your policy might be a smaller model. So you want to be able to, you want to have the ability to precisely tune what GPUs go to what job, right? Because obviously the smaller model needs less GPUs, and the bigger one you want to give more. So we have these 2 heterogeneous jobs that run in parallel. These 2 jobs coordinate asynchronously. So this means that they're largely independent, and when they do share communication, for instance, the generation results and the log probs, that communication process happens asynchronously. But because these 2 jobs run independently, we're able to maximize the GPU performance because they're asynchronous and because we can precisely tune the number of GPUs per model. So to perform the communication, we use this software called PyTriton, which is a LLM serving framework that NVIDIA has part of its NeMo, broader NeMo framework. Another detail is that for each job we have 2 models, right? We have the ability to dynamically switch between these 2 models. So let's say you're doing some inference on the value model and you need to do some forward passes on the reward model. In order to minimize GPU idling, we on demand swap the rates. So we push the value model to host, and we load the reward model onto GPU at runtime. And this, because it reduces the amount of jobs, it simplifies the orchestration of these models. It really improves overall the GPU utilization. The next feature I'll be talking about is our ability to use TensorRT-LLM for inference. So TensorRT-LLM is another software that's part of the broader NeMo framework. And in particular, it's it's NVIDIA's solution to perform really fast production level quality inference serving. So as Gerald mentioned, there's this really big inference stage where you have to sample your model with a lot of generation. In fact, this is the bulk of the computation of RLHF. So if you want really great performance, you have to make sure that you have really great generation performance. So the way we do this is that we use TensorRT-LLM. So we take our NeMo model, which is doing training, and on the first step, we actually create a replica of the model inside TRT-LLM. And because we have this replica model, we can do auto generation inside TRT-LLM. So shown here in the diagram, the TRT-LLM engine will produce generations. The NeMo model will consume those generations and do its training. And then when it does training, it will call its optimizer to step the weights and send those updated weights back to TRT-LLM. So because TRT-LLM is part of the broader NeMo framework, we have really great interoperability between these two frameworks. In particular, we're able to update the weights inside TRT-LLM with really fast, at really fast speed with really low overhead. So this process of switching between TRT-LLM and NeMo and vice versa happens really fast with really low overhead. In particular, the thing we use is called a TensorRT refitter, which consumes the weights that the NeMo model produces, updates its weights, and then has updated weights, produces new generations, and so on and so forth. Another detail that I want to mention is that inference uses a lot less memory than training. And this is because inference is just lots of forward passes, so we don't need things like optimizers or gradients. So when we switch from training stage to inference stage, what we'll do is we'll actually reshard our model parallelism from training to inference to a lower model parallelism. And the reason we want to do this is because typically in inference, we have much higher computational costs because we are in that autoregressive loop. So we want to minimize those communication overheads and maximize performance. And in particular, what we commonly do is that we have the ability to unfold the training pipeline parallelism. So if for training, if we're using some pipeline parallel size, when we transition into the TRT inference stage, we'll unfold the pipeline parallelism and run that as data parallelism. And this really improves our perf. Some other things we do is that, as I mentioned, we'll unload the optimizer and gradients. And for training, because we're doing training, we don't need the engine, the TRT-LLM engine. So we can also unload that as well during training. So overall, the memory footprint of incorporating TRT-LLM isn't much higher than training. And because we are able to have low memory footprints, and because we inherit really good perf from TRT-LLM, this whole utilizing TRT-LLM for inference really gives us really great perf with really not much downsides. The last really important perf feature that I have is how we handle load balancing. So typically when we run at scale, we'll run with some amount of data parallelism. So this means taking the input batch and sharding it evenly across some data parallel workers. For generation, because generation is each generation might have a variable length of tokens generated, right? Because you're just sampling the model. If you give each DP worker the same amount of prompts, you'll get idling. And this is because commonly what will happen is one DP worker will get prompts that cause really long generations, and you'll force the other DP workers to wait. And this is not good because when you wait, you have lower performance. So our solution is to dynamically allocate our data loader from a server. So what we'll do is on the first data parallel rank, we'll have a small server that dynamically pushes like requests from the DP workers. It'll receive requests for work, and it will push prompts to those DP workers. Each worker will like consume those prompts, do generations, and then it will push those generations into like a global rollup buffer. And when we finish inference, we'll rebalance that global rollup buffer for training. And this is great because generally for RLHF, because when we run at scale, we'll have many DP workers. So this is a really effective way to make sure that each DP worker is constantly being utilized, which is great for perf. Yeah, so I've talked about 3 really important perf optimizations. Here in this table, we have a sort of a small ablation where we turn off each perf feature, and you can see each of them gives really great perf. The most important, in particular, the most important perf optimization is indeed like TensorRT-LLM for inference. And that optimization gives us a 7x speed up alone. Overall, our perf uplift against a naive implementation is 15x, which is really big. 15x is huge. It's like if previously your run took a week, you can now finish it overnight. So it's really important to have really great perf. And it's really important for like productivity too, because like now that your experiments run fast, you can also iterate really fast, which we found to be really important. This is the same data as the previous slide, but we present it as a graph. And on a vertical axis, we have step time, and on the horizontal axis, we have like the optimizations we've talked about. And you can see that each optimization sort of targets a different part of the end-to-end time. So you can see that each chunk of the like vertical bar is a different part of the RLHF step time. And you can see that each optimization targets like a different color. And you can see that in our baseline, by turning on all our optimizations, we've shrunk every chunk. So this means that our optimizations sort of target the whole RLHF process like holistically to deliver like really great performance at every part of the process. So perf is certainly very important, but you have to make sure that perf is robust. And one of the ways you want perf to be robust is that you want perf to scale. So this means that if you have thousands of GPUs, you want to make sure that at thousands of GPUs, you still have really great perf. Overall, NeMo-Aligner achieves this. We have we're able to observe a 1.8x weak scaling factor with data parallelism. So this means that, let's say you want your experiments to run faster, what you can do is you can just double the amount of GPUs, and NeMo-Aligner will like efficiently be able to use those extra GPUs and run about 1.8x times faster. So this means that if you have thousands of GPUs, you can use all of them, and your experiments will accordingly also run really fast. And the reason we can get this really excellent scaling is for many reasons, but in particular it's because of the really good dynamic load balancing we have that I talked about in the slides prior. So we not only can scale to thousands of GPUs, but we can also scale to the very largest models. So for NeMo-Aligner, this was like a top priority. And we support scaling to the largest models by supporting 3D model parallelism. So for both training and inference, we support 3D model parallelism. So we can do data parallelism, tensor parallelism for intra-node scaling, and pipeline parallelism for internal scaling. So because we have like this really great scaling from 3D model parallelism, we can make sure that even if your model is really large, we can always fit it because we have these ways to shard the model into like over hundreds of GPUs. As an example, here we've shown us training Llama 405B, right? So we have a 405B actor, a 405B policy, a 405B role model. We run this on 1,000 GPUs, and we still get really good perf. Yeah, so all in all, I want to highlight that NeMo-Aligner is really fast. We implement all these data alignment algorithms with excellent performance. In particular, RLHF in NeMo-Aligner is faster than any other open source RLHF implementation to our knowledge. NeMo-Aligner's performance is robust, so we can scale to thousands of GPUs to the largest models. We also provide many knobs to tune performance to your particular workload and setup. So for instance, we have 3D model parallelism, which I've described, resharding, this distributed approach to RLHF. We expose many performance knobs so that even if your workload is kind of unique, chances are you'll be able to tune perf with these knobs so that it's also excellent for your case. As an anecdote, in our experiments, we were able to finish a Llama 370B RLHF in just under 2 hours and using only 12 H100 nodes. And this is actually the fastest we've ever seen RLHF performed. Yeah, I'll give it to you. Yeah.
Thanks. So to conclude things, for future work, we're obviously going to look into more alignment techniques. In particular, one thing that's of interest is doing knowledge isolation during alignment. And this proposes new challenges because we also have to run a large model inference while doing the alignment process. We also want to apply TRT-LLM generally to other online-like algorithms like reinforced leave one out, rejection sampling. And obviously, we all want to further improve and extend performance. This involves, during inference, faster engine offloading, faster pipeline parallelism using dynamic batching, more work on low precision. And in training, we want to do sequence packing, context parallelism, and also more work on low precision. We also want to explore other modalities as well. This concludes our talk. Our repo is linked here. It's open sourced. We have the docs and paper. And thanks to all the contributors on the paper, and as well Wen-Wen, who's our product manager. Yeah, thanks.